So last time, we talked about functions of the form f of t who had components. So they could be written, say, as x of t, y of t, z of t in their column component form. Or maybe in their row component form as x of t, y of t, z of t. Or in their standard basis form as x of t times the unit vector I plus y of t times the unit vector j plus z of t times the unit vector k. And we call these vector-valued functions, and we spent some time learning about how to graph and visualize them. What we'd like to do in this lecture is to look at how some of the calculus ideas from Calc 1 now apply to these guys. So the first calculus idea we want to talk about is the domain problem. Remember that the domain of a function is the set of input values at which the function can be evaluated. Those numbers you can plug into the function and have its output make sense. And the best way to do this is with an example. Let's find the domain of this vector-valued function. C of t is the vector square root of 2t plus 3, comma, sine of t over t, comma, e to the 2t minus 1 minus 2t, quantity divided by sine of t. So the domain is what you're allowed to plug in. Now let's look at these guys separately. There's this first component function right here. Now we know that for a square root, the number underneath the radical has to be greater than or equal to 0. We can't stick negative values in there. And so that would get me 2t has to be greater than minus 3, or t has to be greater than minus 3 over 2. And I'm going to draw that in interval form. So we have the point minus 3 halves, and then everybody to the right of that would be allowed. And so in interval form, this would be bracket minus 3 halves, comma, infinity. That would be the domain of just this function right here. Similarly, if we take a look at this second guy, well, sine is continuous everywhere, t is continuous everywhere. The only place where this goes bad is at 0. So my domain would look like everything except for 0. So there's an interval picture, or if you want to write it in interval notation, it's minus infinity 0, union 0, infinity. And then there's this last piece right here. This last piece, the numerator is a nice function. The exponential 1 and 2t are continuous. The denominator is continuous and vanishes whenever sine of t vanishes. So we can't have the bottom be 0. And sine of t vanishes whenever you hit 0 or a multiple of pi or a multiple of 2 pi or any of these other guys right here. And so if we were going to go and draw that in terms of a line segment, we would have a circle at all of the multiples of pi, but everybody else would be allowed. And that would be a little bit tougher to sort of write. So that's for each of these pieces individually. What would the domain of this function be? It's got to be the values of t for which all three of them make sense. So we're going to need t to be larger than 3 halves. We're going to need t to not be 0, and we're going to need t to not be any of these other values. So if we put those observations together, then we'd have to say that the domain has to be the set of values t who are greater than and equal to negative 3 halves, about negative 1.5, but it can't be 0, it can't be pi or 2 pi or any of the multiples of pi. If you want to write this in interval notation, we could write this as minus 3 halves to 0, union 0 to pi, union pi to 2 pi, union, and we could just keep going on right here. And so that would be the domain of this function. These are the values we're not allowed to plug in. Next, let's talk about limits, which was the sort of fundamental operation we needed to make calculus work. So what do we mean by this statement right here? Or what do we mean by this expression? The limit is t tends to a of f of t. Or the limit is t tends to a of the vector x of t, y of t, z of t. What should it mean? Now remember that when we write down something like this in Calc 1, the limit is x tends to a of f of x is b. What we're really saying is we're saying that f of x is approximately b when x is approximately a. And if x is really, really, really close to a, then f of x is really, really, really close to b. And so it's an idea as the input is close to a, then the output should be close to some value b. So now if I want to apply that to a vector, well, every time I plug in numbers into a vector, I should get a vector output. So the first thing I want to be able to say is I'd like to be able to say that the limit of a vector-valued function should be some kind of a vector. So maybe a v1, v2, v3. And what we want to mean by this is this idea. So when we say the limit as t tends to a of f of t is the vector v, what we want that to mean is we want it to mean that f of t is approximately equal to this vector if t is approximately equal to a, with the little proviso I should have pointed out last time, that t is not actually equal to a. Remember, limits are what happens around a point right here. But if I write down what f of t really is, it's really the vector x of t, y of t, z of t. So what we're saying is that x of t, y of t, z of t is equal to v1, v2, v3 if t is approximately equal to a. But what does that mean? Well, that means that x of t is approximately v1 and y of t is approximately v2 and z of t is approximately v3 whenever t is close to a. But if you think about it, each one of those statements is what it means to be a one-variable limit. And so this is in fact how we're going to define what a vector-valued limit is. We're going to say that the limit of a vector-valued function is the vectors v1, v2, v3 if the limit of the first component matches the first component of the vector, and the limit of the second component matches the second component of the vector, and the limit of the third component matches the third component of a vector. So a vector-valued limit is really just 3 or 2 if you're in the plane, smaller limits worked out. Let's try this out on the example we just looked at. Let's reconsider the function, the vector-valued function square root 2 plus t, comma, sine t over t, comma, e to the 2t minus 1 minus 2t over sine of t. And now let's take a look at a particular limit. Let's take a look at the limit as t tends to 0. So according to our definition, this just means we're going to take the limit component-wise. So we'll take the limit as t tends to 0 of the square root of 2t plus 3. We'll take the limit as t tends to 0 of sine of t over t. And we'll take the limit as t tends to 0 of e to the 2t minus 1 minus 2t over the sine of t. We'll have 3 separate limits to work on, so let's handle them one at a time. This first limit is really easy. Remember our basic technique from Calc 1 and Calc 2 is that for elementary functions we plug it in. So in this case, I'll plug in t equals 0, I'll get the square root of 2 plus 3, which is the square root of 3. And as long as this value is a number, then we know that 0 is in the domain of the function and that elementary functions are continuous on their domains. So that tells me that the first component of this vector has a limiting value of 3. Now let's focus on the second bit. If we take the limit as t tends to 0 of the sine of t over t, well, if we plug in, we're going to get sine of 0 over 0, which simplifies to 0 over 0. That's not a real number, and so I can't give you an answer just yet. In fact, this is an indeterminate form. However, it's precisely the kind of indeterminate form that you could use L'Hopital's rule on. So if we were to go and apply L'Hopital's rule, remember how L'Hopital's rule works. It says you differentiate the numerator, so we'll get cosine of t. You differentiate the denominator, so you get 1, and then you reapply the limit. So if I start the whole limiting process all over again, we'll plug in t equals 0, we'll get cosine of 0 over 1. That simplifies to 1 over 1, which is the real number 1. And since we got a real number, we know we're in the domain of this, and that becomes our limiting value. So now I know that the second component wants to tend to 1. Lastly, let's take a look at this third component right here. So we'll compute the limit as t tends to 0 of e to the 2t minus 1 minus 2t over the sine of t. So if we plug in t equals 0, we're going to get e to the 0 minus 1 minus 0 over the sine of 0. Sine of 0 is 0. E to the 0 is 1. So we get 0 over 0 again. This is an indeterminate form. It means I have to go and apply L'Hopital's rule. So if we apply L'Hopital's rule to this limit, we're going to get the limit as t tends to 0. We differentiate the top. The derivative of e to the 2t is 2e to the 2t. The derivative of 1 is 0. The derivative of minus 2t is negative 2. Then we differentiate the bottom. We're going to get cosine of t. So if we go and we plug in our value of t, we're going to get, 2 times e to the 0 minus 2 over the cosine of 0. So that's 1 on the top. So we're going to get 2 minus 2 on the top, which is 0. Cosine of 0 is 1. And 0 over 1 is the real number 0. So since that's a number, that's going to be our limiting value. And so now we have each of the 3 components. We're not done, of course. We've got to put this back in a vector. So what's our limiting value going to be? it's going to be the limit of each of the components separately. So the limit as t tends to 0 of c of t is going to be the vector root 3, 1, 0. Let's take a look at one of the most important limits from Calc 1, the derivative. So if f of t is a vector-valued function, what's f prime of t? Well, remember the definition for derivative in Calc 1. It was the limit as h tends to 0 of f of t plus h minus f of t over h. Well, we could steal that and apply it to vector-valued functions. Does such a thing make sense? Well, let's see if we can write out what this object would be right here. So this is going to be the vector x of t plus h, y of t plus h, z of t plus h, that's the first part of the numerator, minus x of t, y of t, z of t, all divided by the real number h. But remember that vector subtraction is component subtraction. So this is going to be the limit as h tends to 0 of the vector, of the vector x of t plus h minus x of t, y of t plus h minus y of t, and z of t plus h minus z of t, all over h. Remember, h is a real number, so to divide a fraction by h is to scale it by 1 over h. So let me write it like that real fast. All right, this is scaling it by 1 over h. And if I actually were to scale each one of those components, I would get this, the limit as h tends to 0 of x of t plus h minus x of t over h, y of t plus h minus y of t over h, and z of t plus h minus z of t over h. Lastly, we just talked about how you take vector limits. When you take the limit of a vector, you just take the limit of each piece separately. So I have 3 smaller limits right here. And if we look at these limits, this first limit, the limit as x of t plus h minus x of t over h as h tends to 0, that's exactly what x prime of t means. Similarly, the middle term is exactly what y prime of t means, and the last term is what z prime of t means. And so what we've just shown is how do you differentiate a vector-valued function? You differentiate each piece separately. In other words, if f of t is the vector x of t, y of t, z of t, then f prime of t is the vector x prime of t, y prime of t, z prime of t. And we also write this as df dt of t, just like we did in the Calc 1 class. We can use the dd notation or we use the prime notation. So let's test this out on an example. Let's find the derivative of the vector-valued function r of t equals t squared plus 1, comma 2t at t equals 2. So notice that this is a plane curve, not a space curve, but the principle is still the same thing here. If we want to work out r prime of t, all we have to do is take the two components, t squared plus 1 and 2t, and we just need to differentiate them one at a time. The derivative is component-wise. And so if we differentiate, well, the derivative of t squared plus 1 is going to be 2t. The derivative of 2t is just going to be 2. And so there's my derivative. Now, if I want the derivative at t equals 2, well, we'll just plug in time equals 2 into my formula, and I'm going to get 4, comma 2. And so there's my answer. Nothing to it, right? We just take derivatives and we plug in. That's not the real purpose of this example. This example wasn't to show you that you're good at taking derivatives again. I know that you're good at that. What I want to do is I want to give you some physical meaning behind what this vector 4, 2 is. And so to do that, I want to start off by graphing this particular function right here. So let's make a quick plot of this guy. If I were to go and say plot some points, I'll set up a t, x, and y table of values. say -2, -1, 0, 1, 2, 3. And so if I were to go and plug these ordered pairs in, when t is equal to -2, the x value would equal 5, the y value would equal -4. When t is equal to -1, the x value would be 2, the y value would be -2. At 0, we would get 1, 0. At 1, we would get 2, 2. At 2, we would get 5, 4. And at 3, we would get 10, 6. So let's go and make a plot of this. So here are the points we've plotted in increasing order of t. If I were to smoothly connect those following the flow of time, I would get an object who looks something like this. A parabola turned sideways. Now imagine I were to go and plot this vector in green right here, the vector 4, 2. If I plot it in standard position, 4 units over, 2 units up, I would get this vector right here. And that doesn't seem like it has anything to do with what's going on right here. Well, remember, in Calc 1, one of the things we used the derivative for was to talk about the slope of a curve at a particular point. So instead of drawing this vector at some random point, let's draw it at the point who corresponds to t equals 2. If I were to go and draw a vector right here who goes 1, 2, 3, 4 units over, and then 2 units up, I would draw you this vector right here. And heck, if that doesn't look extremely tangent to this particular curve right here. Let's try this for another point just to see if this works all the time. What if we instead worked out r prime of -1? So here's our derivative formula. R prime of -1 would be the vector -2, 2. So let's go down to our curve right here, and let's draw a vector who goes 2 units to the left and 2 units up. That would be this vector right there. And once again, that seems pretty tangent to the curve. Just for one last example, what if we did r prime of 0? Well, r prime of 0 would be the vector 0, 2. Now, if we were to go right here to 0, which is the point at which the graph bends, the vector 0, 2 would be this vector right here. And so what we're seeing in this particular example is a general trend, that the derivative vector, if drawn at the appropriate point on the curve, will always be tangent to the plane curve. The derivative vector is a tangent vector at the point in question. That gives me an idea. Find the equation of the tangent line to the space curve h of t equals cosine t sine t at t equals 5 pi over 6. Now, although we don't really need it for this, remember what this curve was? We looked at it last time. This was the curve who described a helix, a spiral around the z-axis that sort of worked its way up and down the z-axis. I'll put some arrows on so we can get some flow to it right here. So what we want to do is, at the value t equals 5 pi over 6, which maybe roughly corresponds to, let's see, 5 pi over 6. In my head, that's 150 degrees. So that would be time equals 150 degrees. So we'd be looking at a point, say, roughly over here. Right, a point this is time equals 0, and so at time equals 5 pi over 6, we'd be a point right around this area. And so we want to find the equation of the line tangent to this space curve at this particular point right here. Now that seems like there's a heck of a lot going on here, but let's just do it in small pieces. To find the equation of a tangent line, I only need to know 2 things: a point on the line and a vector parallel to it. Now the point of tangency has already been told to me. We want it to be tangent to this space curve at this point. So the point of tangency is just going to be h of 5 pi over 6. So if we work that out, we're going to have as my point, or my vector point if you'd like, the cosine of 5 pi over 6, the sine of 5 pi over 6, and 5 pi over 6. And if we were to work these values out, I'll give myself a little bit more room. So let's see, the cosine of 5 pi over 6, that's a 30-degree angle in quadrant 2. In quadrant 2, cosine is negative, and the cosine of 30 degrees is root 3 over 2. Sine of 5 pi over 6, that's 30-degree reference angle, quadrant 2. In quadrant 2, sine is positive, and the sine of 30 degrees is 1 over 2. That came out looking terrible. Let's fix that. And then finally, we have 5 pi over 6. So this is the vector output, but I want to think in the back of my head that this is really the point on the line we're working with. Next, I'm going to need the vector who runs parallel to this. Well, I'm looking for the tangent vector. That's the direction that this line needs to go. So the vector v that we're looking for has got to be the derivative at 5 pi over 6. So let's take the derivative first. The derivative of this is going to be negative sine of t, cosine of t, and the derivative of t is 1, and then we'll plug in t equals 5 pi over 6. And so the vector that we're going to get is negative the sine of 5 pi over 6, which is negative 1/2, the cosine of 5 pi over 6, which is negative root 3 over 2. Sorry, I had a brain fart there. And 1. So now that I know the vector that's parallel to the line, and I know a point on the line, I could write down either one of the different kinds of equations for a line we've got. For example, if we want to write the parametric equations, x, y, z equals, well, we're going to have x naught, y naught, z naught, so minus root 3 over 2, 1 over 2, 5 pi over 6, and then we'll add our tangent vector, so we'll have negative 1/2, negative root 3 over 2, and 1, and then we'll multiply those by t's. And that's kind of nasty, so let me clean that up a little bit. We have x is equal to negative root 3 over 2 minus 1/2 t. Y is equal to 1/2 minus root 3 over 2t. And z is equal to 5 pi over 6 plus t. And there's the parametric equations of the tangent line. Find the derivative vector to the curve given by the parametric equation r of t equals t times the vector t minus 3, t plus 2 at the point minus 2, 3. Well, since I'm looking for a derivative vector, let's go and compute it. Notice that r of t is t times t minus 3, t plus 2. Well, this t is a real value. It's a scalar. So I can distribute it in and write r as t squared minus 3t, comma t squared plus 2t. And that means that r prime of t is equal to 2t minus 3, 2t plus 2. However, this is where this problem is a little bit different from the one we just looked at. In the previous example, we had to find the derivative vector at a time, t. But now I don't have the time t, I only have the point. So what value of t do we need in order to make this work? Well, I know that the curve r of t is supposed to pass through the point minus 2, 3, which means that at some point, the position vector should be the position vector minus 2, 3. So if I write that in terms of its x and its y components, that means that the x component, t cubed, or t squared minus 3t, had better match minus 2 for some t, and the y component, which is t squared plus 2t, had better be 3 for some value of t. So can we find one value of t that satisfies both of these equations? Well, let's just go and solve the two equations individually. The top equation, if I move everything over to the left, is t squared minus 3t plus 2 equals 0. This can be factored into t minus, not t minus 3. How about t minus 2 and t minus 1? Which means that the top equation is satisfied for time equals 2 and time equals 1. On the other hand, the second equation takes the form t squared plus 2t minus 3 equals 0. So that means that if we factor it, we can factor this into t plus 3 and t minus 1. That one will work. And so that means that either time is equal to minus 3 or time is equal to 1. So we're looking for one common value of t who satisfies both equations at the same time. And it's looking like t equals 1 is the value that does it. And I could double check this. If we plug in 1, we get r of 1 is equal to 1 squared minus 3 and 1 plus 2. And so, yes indeedy, we have a check. So now I know the value of t. Thus, the derivative vector we're looking for is r prime of 1, which in this case will be 2 minus 3, comma 2 plus 2, or the vector minus 1, 4. Now, it turns out that a lot of the formulas we took for granted in Calc 1 have analogues in the Calc 3 setting. For example, if you had two vector-valued functions, so you had two space curves, and you wanted to differentiate these guys, well, then you could just differentiate each curve individually. Another rule that we use an awful lot in Calc 1 is if you had a function and you multiplied it by a constant, then you could pull the constant out. And it turns out that this is also true for vector-valued functions. What about the product rule? Well, remember, there's three different ways to do a product with vectors. One of the ways to do a product with vectors is to take a vector times a scalar. So what happens if you have a vector-valued function times a scalar? Well, the normal product rule would say it should be s prime of t times f of t plus s of t times f prime of t. Does that actually work? Well, let's take a look here. Suppose we had a scalar, so like a function from Calc 1 times a vector-valued function. So let me write this as s of t times a vector-valued function x of t, y of t, z of t. So s of t, f of t is this guy, and if I scale everything through, that'll be s of t, x of t, s of t, y of t, and s of t, z of t. So now imagine we go and differentiate this. So if we go and differentiate this, well, we're going to take the derivative component by component. So if I differentiate the first component, since that's now a function from Calc 1, we can go and use the regular Calc 1 product rule. That will get me s prime of t, x of t, derivative of the first times the second, plus the first times the derivative of the second. And then if we do the same thing on the second row, we'll have the first times the derivative of derivative of the first times the second, plus the first function s of t times the derivative of the second y of t. And last but not least, we'll have s prime of t, z of t, plus s of t, z prime of t, by doing the product rule to each of the three component functions. Now, if you stare at this long enough, I could rewrite this as, since vector addition is done component-wise. But now notice that everything in this first component could be scaled. I can scale out an s prime of t from all of these terms, and I'll just have x of t, y of t, z of t left over. On the other hand, in the second vector, I could factor out an s of t, this common factor, and I'll be left with x prime of t, y prime of t, z prime of t. And if you take a look at what this is, we have s prime of t times x of t, y of t, z of t, that's the function, plus s of t times the vector x prime, y prime, z prime, which is exactly the derivative f prime of t. So it turns out that the product rule does work in this situation. What's another product we looked at? The dot product. So imagine we were trying to take the derivative of one vector-valued function dotted with another vector-valued function. This was another kind of product we looked at. Well, my guess would be I take the derivative of the first function dotted with the second plus the first function dotted with the derivative of the second function if the product rule is supposed to work. But that's a big if. Does it in fact work? Well, let's test this out. Let's say that the function f is x of t, y of t, z of t. And let's say that the function g is u of t, v of t, w of t. So their dot product would be x times u, and I'm just going to leave off the t's right now, plus y times v, plus z times w. So what if I want to differentiate this? Well, if I want to differentiate this, I'm going to have to differentiate each piece separately. Since each one of these things is a Calc 1 function, I'm going to use the product rule on each bit. So if I apply the product rule to the first part, x times u, it's going to be the derivative of the first times the second, plus the first times the derivative of the second. If I apply the product rule to this piece, it's going to be the derivative of the first times the second, plus the first times the derivative of the second. And if I apply the product rule to the last piece, it's the derivative of the first times the second, plus the first times the derivative of the second. But take a look at what we have right here. Let me isolate every other piece for you. If I take a look at x prime of u plus y prime of v plus z prime of w, that's exactly what I'd get if I took x prime, y prime, z prime and dotted it with the vector u, v, w. But x prime, y prime, z prime, that's f prime of t, and u, v, w, that's g of t. On the other hand, we've got these remaining pieces. So we have x u prime plus y v prime plus z w prime. And we stare at that long enough, that's x, y, z dotted with u prime, v prime, w prime. But x, y, z is exactly the vector f, and u prime, v prime, w prime, that's exactly g's derivative. And so once again, we see that the product rule holds. There was one last product we looked at, the cross product. And so if we were to write f of t crossed with g of t, our guess would be that it should be the derivative of the first times, in this case, cross the second, plus the first crossed with the derivative of the second. I'm not going to derive this one, but it is true. It's just a little bit more horrific than the other ones. It is worth noting, you better get the order right when you're dealing with the cross product. The one last rule that we used an awful lot was the chain rule. And so the chain rule, we could write it like this. We could say, suppose we had a vector-valued function of some other function. F of h of t. Well, if I were to use the chain rule from Calc 1, it would be f prime of h of t times h prime of t. Now, if you think about this, though, the input right here has to be real for this composition to make sense. So this value right here has to be real, whereas this value right here is vector valued. So I ought to point out that writing it like this doesn't make sense. We always stick constants in front of vectors, so I really ought to write it like this. If the chain rule from Calc 1 is supposed to carry on over into Calc 3, this is what the chain rule has to look like. And I'm going to leave it to you as an exercise to show that it does work. Well, the last of the main limits that we talk about in Calc 1 is the integral. And so it's natural to ask, if you have a vector-valued function f of t equal to the vector x of t, y of t, z of t, then what's the integral of f of t dt? Well, given what we've seen so far, you want to take the domain, you do it component-wise. You want to take a limit, you do it component-wise. You want to take an integral, you do it component-wise. It makes sense that if you want to integrate a function, you integrate it component-wise. What about if you have limits for integration? Well, again, you do it component-wise. I'm not going to get into the theory behind this. It just seems like it's the natural thing to do right now. And if you want to go back and work your way through the Riemann sum definition, which is the official limit definition, you'll find we get exactly this. Let's just start off with an example instead. Compute the antiderivative of the vector-valued function 2t squared I plus t sine t squared j plus t e to the 4 t k dt. Well, since this is a vector-valued function who has an x component and a y component and a z component, we can simply integrate these three pieces separately and write down our answer. So let's do that. If we do the first integration, we're going to get the integral of 2t squared dt. That's just a basic power formula. We'll up the power by 1, we'll divide by the new power, and there is one antiderivative, and we add a constant to make sure we hit every antiderivative. Next, let's do the integral of t times the sine of t squared dt. Notice that this is the integration of a product. Integrals of products can be solved by one of three things. You can either expand them out, you use a substitution, or you use integration by parts. In this case, this seems like a good candidate for an integration by parts. If we let u be t squared, then du is equal to 2t dt, or du over 2 is equal to t dt. So this becomes, let's see, t times dt can be replaced by du over 2. Sine of t squared can be replaced by sine of u. And we have a brand new integration problem. So this is 1/2 the integral of sine of u du. The antiderivative of sine is negative cosine. So this is negative 1/2 the cosine of u. And if we back substitute, that becomes minus 1/2 times the cosine of t squared. And we get one antiderivative, and we add a constant to take care of the other antiderivative. Now, it's worth noting that these two constants aren't the same thing. Or at least they don't have to be. They could be any constants. So a lot of times it's traditional to subscript these different constants. There's a C1 for the first component and a C2 for the second component. Last but not least, let's take a look at this last integral, t e to the 4t dt. Once again, I notice that this is a product. Since it's a product, the only things I can do is I can either expand it out using algebra, using FOIL, I can do a substitution, or I can do an integration by parts. This particular setup of t times e to something is a pretty classic integration by parts problem, and I can solve it using a tabular method. So for example, if I were to go and set up a derivative column and an integral column, I'll let t be the thing I differentiate, e to the 4t be the thing I integrate. The derivative of t is 1. The antiderivative of e to the 4t is 1/4 e to the 4t. If we differentiate again, the derivative of t is 0. The derivative of 1 is 0. The antiderivative of this will be 1/16 e to the 4t. And since I got a 0 here, I'm going to stop. So I'll draw my diagonal rungs, one horizontal rung, plus, minus, plus, integral. And then I can read off what this derivative is directly from the table. The first diagonal tells me that we should have positive t times 1/4 e to the 4t. The middle rung says we should subtract 1 times 1/16 e to the 4t. And the bottom rung says we should integrate 0 times something. Well, that's easy to do. So the integral of 0 is the function 0. If I clean this up, I get 1/4 t e to the 4t minus 1/16 e to the 4t. And so we've built a new antiderivative. Of course, I have to add an integration constant and put on a subscript so that we know it's a different integration constant than the other ones. And so now that I've got these three values, we just need to stick them in the appropriate places. And so what we'll have is 2/3 t cubed plus c1 quantity times I, plus negative 1/2 the cosine of t squared plus c2 quantity times j, plus 1/4 t e to the 4t minus 1/16 e to the 4t plus c quantity times k. If I were to distribute this I, this j, and this k to these guys, I could rewrite this as follows. This is 2/3 t cubed times the vector I, minus 1/2 the cosine of t squared times the vector j, plus 1/4 t e to the 4t minus 1/16 e to the 4t times k, plus c1i plus c2j plus c3k. Notice that what this vector is this first component is just any antiderivative of the first part. This component was just any antiderivative of the second part. This component was just an antiderivative of the third part. And this last part right here represents any possible vector. Said slightly differently, we've just shown the following basic fact. If capital F of t is an antiderivative of a little vector-valued function f of t, then the indefinite integral of little f of t dt is going to be that antiderivative plus a vector constant. This piece right here. This is a fact we took for granted in Calc 2, that antiderivatives are unique up to real constants. Well, this just says vector antiderivatives are unique up to vector constants. So we have a nice parallel. A common variation on the previous example is this problem right here. Find the parametric curve that satisfies c prime of t equals 1 plus t comma t squared minus 3 with the initial condition c of 1 equals the vector 1, 2. This is sometimes called a differential equation. The goal is to find a function c of t, in this case a vector-valued function, that has the desired properties. Well, all this really is it's an integration problem working backwards right here. Whatever this first component is, x of t, we know two things about it. We know that x prime of t is equal to 1 plus t, and we know that x of 1 has to be 1. With these two pieces right here, we have more than enough calculus to figure it out. If the derivative of x of t is 1 plus t, then I know that x of t has to be an antiderivative of 1 plus t. So if we integrate this, we're going to get t plus 1 half t squared plus an integration constant. So any antiderivative of 1 plus t takes the following form. But I'm not looking for any antiderivative, I'm looking for this one. If I plug in t equals 1, I should get 1 as an output. So if I plug in t equals 1, what I'm going to get is 1 plus a half plus c. So the only way that that's going to equal 1 is if c is equal to minus 1 half. And so I now know what the x component is. The x component has to be t plus 1 half t squared plus the particular constant negative 1 half. All right, now let's do this for y of t. We know what the derivative of y of t needs to be. It needs to be t squared minus 3. And we also know what y of 1 needs to be. It needs to be 2. And so we can work out what y has to be. Y has to be an antiderivative of t squared minus 3. So that means it's got to take the form 1/3 t cubed plus 3t plus some constant, a different constant than last time. How are we going to figure out what this constant is? Well, that's what the second fact tells me. We know that if we plug in 1 into this formula, if we plug in 1, we're going to get 1/3 plus 3 plus e, but we're supposed to come out with 2 at the very, very end of it. So let's see. We're going to get e has to be 2 minus 3 minus 1/3, so that would be minus 1 minus 1/3 or minus 4/3. So now I know what the value of e is, and I know what the antiderivative is. That tells me that y of t has to be 1/3 t cubed plus 3t minus 4/3. And so there's the function c of t that we're looking for. Here's the parametric curve who satisfies the differential equation. Let's compute the integral from 1 to 2 of the vector-valued function t squared plus 1, comma 1 over e to the t dt. So all I'm going to do is just integrate each one of these pieces separately and then convert the answer into a vector. So let's go and look at the first component, which would be the integral from 1 to 2 of t squared plus 1 dt. So we use the fundamental theorem of calculus. I just have to find an antiderivative for t squared plus 1 dt, and then I can evaluate that from 1 to 2. So an antiderivative of t squared plus 1 would be 1/3 t cubed plus t, which we can evaluate from 1 to 2. So that's going to get me 1/3 of 8 plus 2 when I plug in 2, and then it's going to get me 1/3 of 1 plus 1 when I plug in 1. So let's see, that's a grand total of 8/3 plus 2 minus 1/3 minus 1. Notice that 8/3 minus 1/3 is 7/3, whereas 2 minus 1 is plus 1, and that gives me a grand total of 10/3. On the other hand, if I want to go and integrate from 1 to 2, 1 over e to the t dt, the fundamental theorem of calculus says, well, the first thing I should do is find an antiderivative of 1 over e to the t dt, and then I can worry about those two limits. Now, there's no clever integration tricks for dealing with a quotient, but one of the first things we do in calculus, the first step, is we prep things. This integral right here could be rewritten as the integral of e to the minus t dt, evaluated from 1 to 2. And this is actually one of our basic integration formulas. This is one of the basic 20. So if we use our formula, the integral of e to the kt is 1 over k times e to the kt, evaluated from 1 to 2. So we plug in 2, we're going to get negative 1 times e to the negative 2, take away, when we plug in 1, we're going to get negative 1 times e to the minus 1. And that gives me a grand total of negative and negative is positive, 1 over e minus 1 over e squared. So now that I know the two component parts, I now know the answer. The integral of a vector is the vector of its integrals. So the integral of the first component will be 10/3, and the integral of the second component will be 1 over e minus 1 over e squared. And so there's my answer. The only thing I want to point out about this is that whatever this integral is measuring, it's not measuring areas under curves anymore. To see this, just note that whatever this thing is right here, it's some kind of a plane curve. And I'm not going to try to draw it accurately, I'm just drawing this for illustration purposes. It's some kind of a plane curve, who knows, maybe it goes like this from one point, oops, I drew my arrow the wrong way, say from this point to this point to this point. So we might have, say, a time equals 1 right here and a time equals 2 right here. And so we might think about the area underneath this curve. Well, whatever that integral is, whatever this area is, it should be a real number. But whatever the integral of a vector-valued function is, it always comes out being a vector. So this thing is not area under a curve. Whatever the area under a curve is, it's got to be a number, and this isn't it. So the obvious question to ask is, what is this thing measuring? To be honest, I can't give you a good geometric meaning. This is one of the places where, as we generalize functions, we can still do the operation. It makes sense to talk about an integral. But we've lost one of the meanings. It's no longer the area under a curve. This is just an example of something we can do, even though it doesn't have a physical meaning anymore. In the next lecture, we're going to be able to at least occasionally interpret what this kind of an integral is telling us. But for right now, we're just going to have to treat this as, hey, I can do it, but I have no idea what it's telling me.